applies at so-called leading twist level, neglecting corrections suppressed by powers of the corresponding hot scale. So maybe these are such high twist corrections should reduce this cutoff. A promising approach has been proposed by Key and Witty in relation to virtual photon and proton scattering on heavy nuclei. And in addition to usual diagrams, you have those ones. Look, it's no longer binary scattering. You have a parton here, but you have any number of gluon pairs entering from the other side. What we did, we extrapolated this approach to hadron proton and light nuclei scattering. I will not go in details, you may check the corresponding papers. The treatment involves one single adjustable parameter which controls the magnitude, overall magnitude of such corrections. And very importantly, this parameter, this magnitude, is severely constrained by Faraday. Because you see, the impact of this effect, the difference between dashed blue without and solid red with, is significant for relatively low photon virtualities, whereas it vanishes when we go to highly virtual photons. If one makes this correction stronger, one will fail to describe Q-squared evolution of structure functions. And actually, it's a reflection of well-known fact. Evolution of structure functions is well described by the Kshintsar-Krivov-Lepatov Altarelli-Parisi equations, leaving little room for high twist or for saturation effects. Just people usually don't check such consequences. No wonder we don't have a strong effect on the cross sections. But the mechanism does its job. Look, the jet spectra, they start to flatten in the small PT. Comment. This has nothing in common with the parton saturation. You may also check a few slides in the backup. Rather, it resembles, to some extent, the well-known Landau-Petrachuk-Migdal effect in quantum electrodynamics. Another rather technical improvement, treatment of the pion exchange process. Well, as I demonstrated a dozen of years ago at this very same conference in Berlin, assuming a dominance of the pion, the channel pion exchange over rho exchange enhances the shallow muon content by approximately 20%. Okay, these are different muon thresholds and energy dependence. You may ask me why. It's a direct consequence of the isospin symmetry. If we consider usual central production of rho mesons, they are produced in proportion 1 to 1 to 1. And take into account their decays, we have energy partition between the products of the decay, charged and neutral pions, in the proportion 2 to 1. When we do the pion exchange, for example, in pion nucleus scattering, for example, we have incident pi plus. We only produce rho plus and rho zero polar. We don't have rho minus. And then this energy partition changes to 3 to 1. Much less energy goes into electromagnetic particles. Much more energy is kept in the hadronic cascade. No wonder you get more muons. But the crucial thing here, one has to predict how this mechanism depends on energy. The point is, you only have this mechanism of importance when you don't have any additional elastic rescatterings, which would eat the energy from the final. I'll come back, I'll explain why I speak here about proton neutrons. You can imagine here pion and rho. It's the same mechanism. And those blobs, blue blobs, indicate symbolically the corresponding corrections, the so-called rapidity gap survival factor. Now I want to stress, it is one and the same mechanism which produces raw mesons in pion-proton or pion-nucleus scattering, and which produces forward neutrons in proton-proton scattering. And because of this, and thanks to our LHCF colleagues, one can test and check whether this energy dependence driven by such corrections is properly described. And you may check backup slides regarding this. Air showers. It was a big surprise for me. After having all these improvements, all this work, quite some years of work, there have been only minor differences for predicted air shower property. Something like X max goes up to 10 grams deeper, muon number goes something like 5% down. Why? Are we constrained by the data, or there is some framework which is common to both your models and one simply doesn't go beyond? Well, the question is not of academic interest, because we have, as discussed at this conference, a number of puzzles. The muon puzzle, but in my eyes, much more important is a certain tension between the average maximum depth of our showers and the corresponding fluctuations. If you look at these trends, in both cases, the data indicate a change towards a heavier composition. Yet, sigma X max implies a quicker change, at least when using my model. How to correct situation? One cannot do much with the fluctuations. That's what we stated already 16 years ago in our work with Venya Berezinski and colleagues. One can only try to reach deeper X max. How much is needed? The studies by the Pierre collaboration indicate that one needs a lot, around 50 grams. Is it really feasible in view of LHC data? Well, one has to check. One has to study model uncertainties. But before doing so, one has to identify, to define what we would call model uncertainties. For example, if you forget about energy conservation, we may get practically any answer, but this will be meaningless. If you speak about muon content of our showers, almost of equal importance is the conservation of the isospin symmetry. Not absolutely precise, but very precise. Because, for example, if you forget about it, we can really produce more abundantly charged pions at the expense of neutral ones and enhance muon number as much as you want, which would be equally useless. So in my study, I have 3 basic principles: staying with standard physics, considering microscopic changes in the model, not just changing by hand macro characteristics, and checking consequences. I start with the muon number. But first, as the first step, let us try to define which kinematic range of hadron production is of utmost importance for muon number of our showers. Let me for the moment forget about any secondaries except pions. In such a case, I can write down the muon content of a proton-induced shower as a convolution of muon production spectrum and the muon number of pion-induced subshowers. And you see, you have here 2 terms which are competing. Pion production explodes in the limit of small pion energies. On the other hand, if you produce energetic enough pions, They have subshowers, which give a large contribution to the muon number growth. We can quantify this competition, approximating the production spectrum using such analysis. Here you see this dotted approximation of the Siebel spectrum. And yes, assuming that muon number of pi-induced subshowers follows a parallel, we immediately get such a simple formula. You see. And for typical parameters of the fit, we obtain that the largest contribution comes from pions bearing approximately 10% of the parent proton energy. One can easily repeat the same exercise for pi-induced subshowers and obtain similarly large value of X, of energy fraction of secondary pions, which are important. Well, moving further, we can now include back other stable hadrons like kaons, antinucleons. We have the key quantity, which defines the shallow muon content like this, which can be well approximated by the total energy fraction taken by all the stable hadrons produced. You see, it's very important. People always speak about multiplicity. What defines muon content is not the multiplicity of secondaries. It's the energy fraction taken by all the secondary stable hadrons. Okay, so if you want to increase the muon number, what are the ways to do it? Well, we can try to go traditional way and to increase the multiplicity. Not very efficient, but we can try. And since the energy rise or the multiplicity is driven by miniature production, therefore, by the gluons mostly, then we can play with the gluon density of the pion. Second thing, as I mentioned, of special importance is the pion exchange process. We can try to change its energy dependence to have a larger forward yield over mesons. Well, last option, we can try to produce more stable hadrons, like more kaons, more nucleons, antinucleons, which would increase this quantity. First option. In principle, there are quite some experimental constraints on the gluon density of the pi, most notably from measurements of the valence mark distributions, but also from studies of direct photon and J-type production. But we want to try something. Let's forget for the moment about these restrictions. And we reduce the momentum in valence quarks by as much as a factor of 2. And the free momentum goes into gluons and C quarks. And you see the difference, the default and such enhanced glue. For the muon number, we win less than 1%. Why? Because this mostly impacts highest energies in the cascade, and all interactions at lower energies are weakly affected. We go next. Actually, very interesting. We want to enhance the contribution of the pion exchange process at high energies. More or less, the only way to do so, we artificially and physically neglect absorptive corrections. And you see, having the same calibration here, fixed target energies. When we go to higher energies, we have this dashed blue above red, something like maybe 30%. But if we forget absorptive corrections, we have two contributions in the pion exchange process. We have normal inelastic scattering, multiple production, and we have elastic pion scattering, because it's total pion nucleus cross-section. And the second rises with energy. So instead of enhancing the muon content, because here you have almost nothing produced, just from meson and one pion, the muon number goes down. This option is better. The only thing which is left, we can play with the calibration to the data. I happily show that QGS-3 underestimates count production by a huge factor. We can try to correct it and enhance count yields by 40%. Likewise, for antiprotons and protons to match Na61 data, I need to enhance the yields by as much as 60%. Well, you may ask me, why didn't I do a calibration better from the very beginning? Very simple. Hadronization is a universal procedure. If I did so, as you will see in a minute, this blue stuff, one will strongly overestimate count and nucleon yields in proton-proton scattering and even in pion-proton scattering, as you see here. You see this blue, which was needed to better fit Na61 data. It is about factor of 2 above the data of LBC EHA's experiment. But don't mind. We accept these changes and we see what happens. Yes, and also we consider 50% enhancement of raw meson production. In principle, here the model is not that bad, but to improve, okay, let's be generous and produce 50% more. Results. Raw mesons give nearly nothing, because it's a central production, not forward raw meson. And we produce different rows in equal proportion. We don't change the balance between pi zeros and pi pluses, produce it more rows of all kinds. With counts, we get up to 7%. With various nucleons and antinucleons, we approach 10% enhanced. Point. Limit. I switch. How much time do you have? A minute. I quickly switch to the shallow max. Here again, we have 3 main switches. In the first place, Xmax depends on the inelastic cross-section. Second goes the diffraction. And the third one is the inelasticity. Well, cross-section. 2.6% difference between Atlas and Totem at LHC. If you plug these values into the Glauber formalism and calculate proton-nucleus cross-section, the difference will become a little smaller because proton-nucleus cross-sections are governed by the nuclear size. And just to have a value in mind, whenever you change proton-layer cross-section by 1% at the highest cosmic range, you change X max by 1 gram per centimeter squared. Diffraction. I did a study 10 years ago. Typical impact of playing with diffraction, 5 grams. And there is a more recent study to be published soon, but it's still about this level. We are left with an elasticity. No other possibilities. Generally, the elasticity should rise with energy. Because the higher energy we go, the more multiple scattering we have, the more hadrons produce, and they eat the energy from the parent proton. Yet, one might try to choose softer spectra for them, such that the new hadrons don't eat too much. And the main, or maybe the only possibility is to play with the distribution of so-called constituent partons, which work as 3 nets, having such an exponential distribution and playing with the corresponding exponent. In the limit of 1 over x, alpha equal unity, one will have something like this, producing a lot at central rapidities, but having soft spectra forward and back. But this, as we shall see in a minute, may not work for mini-jet production. Okay, just doing a calibration of the model, having more or less the same description of accelerated data for all the options we consider. Interestingly, if we consider data of CMS and totem, moving to this of the distributions, decreasing alpha, we get the distribution forward falling quicker and quicker. So in principle, the trend is not really supported, but not yet disfavored a bit in the accuracy. Yes, and doing some combination forward and central, one would have better discrimination possibilities. So what do we get? Indeed, we get a slower energy rise of the inelasticity. It is reduced up to 6% at the highest energy. How much do we win for X max? 10 grams. Why? Why such a moderate effect, both on elasticity and on X max? Very non-trivial, because you have perturbatively produced particles, the ones you are able to calculate, the ones you are able to predict. And if you sum up the energies of all these particles, they make the lower limit, lower bound of the inelasticity. Well, in principle, I would have stopped there, but being just open-minded, I consider exotic option. I assume that hypothetical collective effects suppress parton cascades, eliminate them. Instead of having a picture like this, we are left just with partons produced at central rapidity. And we play again with these string distributions. What do we get? Drastic effect. Elasticity is reduced enormously, in particular in the limit for this alpha equal 0.9, approaching the 1 over X behavior. It is just energy independent, above 1 PV. At energies where one is dominated by miniature production. And yes, we get much stronger impact on X max. In this, I personally believe, pretty unphysical way, up to 25 grams. But this is really the maximum you get. It's already under crazy assumptions. Well, with the data, actually difficult. One has only, this is only disfavored by LHC data. You see, moving to this larger alpha, you have higher and higher yields of large XF neutrons, of highest energy neutrons. And thereby you underestimate the inelasticity of neutrons. Much more severe restrictions come from the PRG collaboration, from the muon production threshold. Because whatever you do change in X max, the effect on the muon production maximum will be at least as high or even higher. Here, things are moved deeper by 30 grams. Okay, you can read my conclusions from the screen. Thank you for that attention.
Thank you very much, Sergey. So we have time for questions.
Very nice, Sergey. Something I didn't get. You said that the whole change increased the number of muons by 20%, and at the end you say you have only 5%. Or where did you lose your? What happened? I mean,
you speak about muon number.
Yes, you said the pion exchange will increase the muon by 20%, but then you said at the end it's only 5. So
no. Pion exchange is well defined. We have the data, we have the energy dependence. There is no freedom. But if we want to change the energy dependence, whatever, we assume that the gap suppression is not as strong as it is done. If we have weak repeated gap suppression, we have two contributions. In the usual case, this process disappeared because repeated gap suppression, this factor, pushes pion exchange process to the periphery, to large B's. where this becomes unimportant. If you don't have these corrections, we have both contributors. And this kills the effect, actually makes the opposite one. The muon number falls down instead of rising.
Okay, so it's because it's just because on your side you said 20% more muons.
Yes, if you do it,
If you don't do,
if you do it, and if you do it right way, you have 20%.
but then you have the elastic.
Which were already included too. Okay, if you do it wrong, you get less muons. Actually, muon number falls down.
Yeah, so then I don't understand. Can you come back to your
Yes.
if you go back? Yeah.
You see, this stuff, let me just see. Okay, this is neutron NPP, but you have the same for pion, same process. We have these guys. These are huge corrections, huge probability to have additional inelastic rescattering. Once we add small impact parameters. In order to have this damping factor weak, we have to go to the periphery. And there, one is eliminated, like shown here, by a single pomeron exchange. For elastic scattering, we need two pomerons, you know. And this disappears at large B.
So the elastic disappear.
Yes.
Yes, so it should be good for the muon production.
Here, there is no elastic. There is only one pomeron exchange. But because of these corrections, which help us, the probability slowly decreases with energy. In the other case, I want the probability of the process to rise with energy. I neglect all these factors. And immediately I get back the elastic, which kills the whole thing.
Okay, so it's more complex.
We discuss. Yeah.
Okay, is there any other question?
Thank you for the talk. So you say that the Xmax changes. How does it compare with the real data? Because when you simulate, you can change the Xmax,
Yes.
but with the data,
Thank you for the question. Real data require Xmax to go deeper by 50 grams. What I showed, doing reasonable assumptions, you don't get more than 10 grams shift. If you go crazy, you get 25 grams, half of what is required here.
thank you.
Any other question? There are two there.
Just an additional comment on that. You need 50 grams if you don't change the number of muons. If you change the number of muons at the same time, you need probably not need 20 grams. So.
Okay. You know better how much one needs.
Thanks for your presentation. There is experiments that measure the pion branching ratio to either mostly muons, right? But there's this suppressed channel that goes into either positrons or electrons, depending on the charge. So how those experiments that measure that branching ratio affect your model?
In no way.
Not at all?
I produce pions and then I have the decays.
Right.
I don't modify branching ratios.
Okay.
For
Just
me,
wondering if that somehow affects
no.
your tutor. Okay.
It'd be too much.
Okay. Is there any question online? I don't have questions online. So okay, so let's thank Sergey again.